transformation that at the end of the day, I get linearizability, right? I want to prove it for all reachable states, so I'm going to do induction over the set of reachable states. I want to prove linearizability. What's going to happen? It's the same thing that always happens.
It wasn't true for some reason first.
Oh, well, okay. So that is true, but that's, although that's frustrating, it's actually a reason to celebrate. So our initial implementation of Raft, right, when we made that system transformer, we had mistakes. And in trying to prove it, we found those mistakes. So that definitely happened. But those were, I mean, it was frustrating, but those were kind of good. There's something else that's related but harder, or sometimes harder, yeah.
Wasn't inductive?
Yeah, right, it's not inductive. Linearizability is not inductive. Just knowing, if all I told you, right, is that you're running all these replicas, and you've been running for a long time, and up until now, your trace has been completely linearizable, right? And now I say you take one more step. Are you still linearizable? Just knowing that fact about the history isn't enough to show that when you take that one more step, the property still holds. So you have to find something that talks about the state at the nodes, that talks about the set of messages in the network that is strong enough to imply itself, and also is going to give us this linearizability. And that property, this internal property, is called state machine safety, right? So when we go to prove linearizability, to get linearizability, what we really prove is we're going to prove, like, well, if I had state machine safety, then I get linearizability, right? And I have state machine safety. So there's a rule for putting these kinds of things together to get these kinds of things. You might have seen before. It has some name in Latin or something. Right, so then we had to prove it. And actually we can go look, I mean, it's not the most, like the structure doesn't necessarily jump out at you from the COT code, but we have this inductive invariant of state machine safety here. Right, and this is the interface to it. So this is part of why, when we were looking at the Raft proof, the end-to-end linearizability proof, we had all those pairs of imports, right? So we have decoupled, right? Every time we have a theorem, in one module, we put the statement of the theorem. And this depends on a bunch of other definitions. But at a high level, what it's saying here, you see the state machine safety host, right? At a high level, what it's saying, let me make that one step bigger for folks in the back row. And so that I can reach it, I'm kind of short. Right, what it's basically saying is that in any network, right, in any state of the world, so here, net's a state of the world, it's not just the network. Sorry for the terminology mismatch with Simple DS. Hopefully you'll keep up or whatever. Basically it's saying for any state of the world and for any host view of a certain event, if in another host view, if those two have the same index, then they have to actually be the same event, right? So it's never going to be the case that there's any disagreement about what happened at a certain commit. Right? That's sort of stable. It'll never change. You can count on it. So we can build that. And then there's a proof of it as well. But we can sort of do these parts when we want to prove this. Now, the trick is that these are not the same level of difficulty, right? So trying to, getting this step weighs in at like 5,000-ish lines. But getting the green part was like 45,000 lines of proof in LTAC, right? So that was a lot of work. And it's not easy stuff. I mean, people who have worked on distributed systems or ever tried to reason about them can tell you these proofs are often pretty subtle, right? The reason the systems work is actually not what you thought at first when you implemented it, right? There's more going on under the hood. Yes?
So was state machine safety a previously existing notion from paper proofs, or was this invented by this proof engineering development?
State machine safety was previously existing. So the inventor of Raft is actually this guy who's very cool named Diego Angara. And in his PhD thesis, so his PhD thesis was about Raft. In his PhD thesis, he outlined several state machine safety properties. It turns out that it wasn't they weren't all inductive. We needed a few more. But actually, a lot of the key invariants for reasoning about the system, we had to strengthen to be inductive, et cetera. But those were, we had really strong lead on that. Good hints on how to start with that. Yes?
So, are you saying in the thesis the proofs were presented without induction, and it's just the definition that's required stronger like induction?
Who said anything about proofs? They were just stated. Yeah, it's like a list. These are the invariants of the system, which a lot of them were. I don't think we actually found any mistakes in those. I think they're all legit. Now, Diego had started writing up a TLA model to model check of this stuff, and he was very interested in applying formal methods, but it was just really hard. Yeah, good questions though. Okay, so now what we want to do is we want to do these two proofs. We've sort of seen these parts. So let's zoom in on how we're actually going to try to prove state machine safety. Now, I've messed up my animations, and so you already know the punchline to the next question, right? But it turns out that if we just take those, those invariants, partially from Diego's thesis, those also aren't inductive, right? So we have to, utter a long sigh and go back to the proof mines and figure out what's an inductive invariant, right? Something that's going to be true initially, it's strong enough to imply state machine safety, and which is true initially and also implies itself, right? It's preserved by all possible steps a system can take in the asynchronous semantics. And so, this is the name of the game. To do this, we introduced a notion of intermediate reachability. We'll talk about that more in a minute. So we had sort of a finer grained semantics, which made some proofs easier, but overall led to sort of more code. In fact, we ended up proving, I think there's something like 90 key inductive invariants to get to Raft's correctness property, but we did it, right? So that ended up working. Now, we can talk more about Raft or maybe even offline, but I kind of wanted to switch a little bit to thinking more about when you're, as an engineer trying to build and verify these systems, what goes wrong? So I've already grumbled about the difficulty of coming up with inductive invariants. And I think that Adam probably hammered this point as well when he was talking about Kami and other stuff. This is just a hard problem. And it's just something that you develop intuition for over time. You get better at it. But it's undecidable, and it seems difficult in practice. It's just hard. There's actually another thing that's sort of more proof assistant specific that was really painful when we were trying to do this verification. Any ideas? Is it anybody? It's something you don't always see when you're working through textbooks. Yeah?
The size of the terms?
So you mean just like the performance of the proof checker? So that definitely led to some problems. And actually, I'll talk more about, we ended up spending some non-trivial effort to try to make proof rechecking faster. And one of our colleagues, called Carl Palmskog, has started sort of a research program focusing on these kinds of problems. So that was definitely part of it. It's kind of a constant friction. But there's something else that's really nasty when you are trying to verify big systems. Yes?
Could it be the difficulty of reusing like certain styles of proof and like just sort of the brittleness of the proofs themselves?
Yeah, so the brittleness of the proofs themselves, right? So when you're trying to build this stuff, right? Every time you prove something, there's sort of two sides to it, right? For all this intermediate stuff. And what happens is, you find some bug in some intermediate step, right? This wasn't quite true. And now you're going to try to fix it. But when you try to go fix it, you have two sides that need to change, right? Basically, the stuff that you were using to establish this fact, if you change this, now you might need to establish slightly different things to get the fixed version, right? And also, somebody else was using this, right? And if you change it, it might not be quite what they needed. So whenever you go to fix a proof, there's these sort of two sides of it that might also need to be changed. But now when you go change those two sides of it, guess what happens, right? That thing also has two sides, right? And you keep going, right? And there's more and more of these little things. So whenever you make a change, there can be these sort of far-reaching consequences that require a lot of updates. And in practice, what we really found is that the main challenge for us trying to verify Raft wasn't necessarily figuring out sort of the theory of the formalization and stuff, right? The inductive invariants were hard, for sure, right? That's a key thing. But what was really nasty was the effort to re-verify the system as we developed it. There's like some Greek thing, I think that, fancy people, some guy had to roll a boulder up a hill forever or something, I don't know. So you kind of feel like that, right? You're stuck doing the same darn proof every time you make a little tweak. And you're nervous when you make a change because you're not sure, right? Even if you got this piece fixed and right where it needs to be, you don't know if there are big consequences somewhere else that are going to cause other things to break in a way that's difficult to anticipate. So, Leonard asked this great question yesterday about what did you do differently? Like, what do you do differently now from what you used to do before you did this proof? And what might be useful for other systems verifications that aren't even necessarily in distributed systems? And so we actually came up with a bunch of ideas. There's this paper at CPP 2016 that sort of details it. But the idea is to really kind of start pushing on proof engineering, right? So when you go to do development of any large software system, there are best practices that you should follow, right? Like, it turns out software engineers have been thinking about this stuff for a long time, and they have a lot of good ideas, right? Like, people working in industry have been building big systems for a long time, and they've learned some lessons the hard way, and we would do well to listen to what they have to say. Now, some of those things we can just pick up and reuse when we want to verify large systems, when we're working in proof assistance, right? So things like information hiding, pretty much you can just take out of the box and reuse. There's a couple of, well, actually, let's have a little discussion about that. So everybody knows this idea about information hiding, right? Abstraction. So when I want to build an ADT, what I'm going to do is I'm going to tell you, okay, there's this type. There are these operations on the type. And here are some lemmas that relate, what these operations do. So you reason about them outside. But I'm not going to tell you how things are represented or implemented, right? You have to just use things in terms of this interface. Why might that be hard in a proof assistant? To have that kind of strict abstraction where I don't tell you any details about how things are defined. I just give you a set of lemmas that allow you to reason about it. Yeah?
Because it's just easy to uncode. The temptation to uncode and improve from first principles is very high.
That's exactly right. So everybody get that? Has anybody else made this point so far at DeepSpec? So here's this thing that happens, right? And you'll notice this all the time when you're doing proofs. Right? How often do you write simple? Pretty often, right? Why do you need to do that? Why is reduction, why is running some of the code in your proof context so important? It's because equality is definitional, right? So things that reduce to the same thing are equal, and it turns out we use equality a lot, right? And so you often want to run things to show that they're equal. It's very useful to be able to do that. But if you hide the definition, right, you keep it abstract, then you can't run it. And so now that temptation, that ability to just unfold a definition, let it evaluate, let it collapse, so you can show equality, you lose that ability, right? And this is not something that traditional software engineering has worried about, right? They're not trying to do proofs in a system where they have extensive use of definitional equality and therefore want to reduce terms when they're doing synthesizing something to ensure correctness. So there are definitely some challenges there with how do you play that game, how do you balance it. But the broad stroke of the idea, right, of information hiding, of abstraction from software engineering is still useful. And when you scale up, it becomes more and more important to be disciplined about doing that, to resist that temptation as much as possible. Now, one thing you can do is you can expose a set of, you can have some lemmas that you expose in the interface that effectively let somebody run the code. And then what you can do is you can change your definitions and the implementations as long as you can continue to provide, right? People can continue to reason about it as if that's how it was implemented. So this gives you some insulation so you can make changes without breaking other parts of your proof. Yes?
Is that running the problem when you use dependent types and it requires things to be definitionally equal?
Yeah. So this works really well in some sort of first order-ish, which for a lot of things it ends up being, right? But when you get something that's rich, in general, we don't use a lot of sort of intrinsic style verification where you carry around predicates with types. Everything tends to be very sort of COMP-cert style, where the implementation is basically like ML code. But so for the intrinsic style, this would probably be harder. That's a great point, actually. Yeah. Okay, so there's stuff like information hiding. You have to tweak that. There's a couple of other ideas that maybe are slightly more specific to systems verification that I wanted to talk about briefly. So one is, how do we get ideas from other verification frameworks into Verity? And another one is kind of maybe more specific to systems verification broadly. So there's this notion of, excuse me, there's this notion of ghost state, right? Have people seen this before? So some verification frameworks provide something called ghost state. And what it is it's basically a write-only part of the state of your system. Now, why would a system ever have write-only state? If you can't read it, then you can't branch on it. And if you can't branch on it, it's not going to affect the behavior of your system. And if it doesn't affect the behavior of your system, what's the point of keeping it around, right? If nobody can ever read this, why would you ever have it? So the reason people, oh yeah, please.
Proofs can read it.
Yeah, exactly. Proofs can read it, right? So in the system itself, the system implementation never uses it. But when you want to reason about what the system has been doing or what it's going to do, it's useful to have kind of a log of all the stuff. So one example of this is, suppose that we're in some term, and the leader has a particular log, right? And it's going to tell some follower to update, right, to agree with it. And the follower is going to have to make some change, right? And maybe in this case, right, the only place that's recorded that this follower saw D is here in its log. And once it does the update, it'll lose that fact. So instead what we're going to do is we're going to also keep some ghost state called all entries that records every entry a node has ever seen, right? So even though when we actually do this update, right, when we actually do it, we're going to lose that fact, we'll still have D in our ghost state. So in the proof, it'll be easy to access the fact, right, that we saw this before, even though it's not going to be stored in the explicit state of the system. Yes?
Have you ever used ghost states to reason about bounded memory systems? So like where you can't have a basically infinite log?
So Raft is not bounded memory. Vardy is not bounded. The Raft transformer introduces potentially infinite, unbounded data structures. Vardy is not a transformer; it's just a system that has potentially unbounded data structures because it's key value store. So if the key type and the value type were finite, maybe it'd be okay. But that's potentially unbounded. The primary backup, it depends on what the underlying system is. So I think all of our big systems have potentially unbounded state. Even the counter system is on NATs. So, so we have other toy things that we use in development, like we have a ping pong system that literally just has 2 nodes that send ping and pong back and forth. So I guess that's finite state. But there's not much to say about it where you'd want ghost state. So are you thinking maybe that for things where you want to ensure you don't run out of memory, or?
Yeah, basically.
Yeah, that could be useful. We haven't looked at that kind of application before, but yes.
So is the ghost state like erased during extraction?
Oh yeah, it's actually going to be, yes it is. But it's actually going to be even better than that in this case. So let's look at how this is actually implemented really briefly in Le Verity. So the ghost state transformer is not in Verity Raft, right? It's in Verity proper because there's nothing Raft specific about having ghost state. What's cool is that it turns out, right, that this ability to have ghost state is really just a system transformer, right? And in particular, what it does is, you remember how like with seeknum, we just added some extra state to every node to track what the biggest message it had sent so far was, so people could see if they were getting something that was stale. Here we're just going to add some extra data, right, that just slapped on to the data that the node already had. And you have a handler that whenever a regular handler runs, you can get access to the ghost state and also update that as well, right? So you have a sort of an extra ghost handler when you get a message, right? And instead of just getting the state, you get both the ghost state and the actual state. And from those, you get to update the ghost state. Similarly with the input handler. And yeah, so in this case, somebody's asking about, well, when I actually extract this, right? This has been all about implementations. I actually extract this and go to run it. I don't want to spend my time updating ghost state that I'm never going to branch on. That doesn't affect the behavior of my system. So how do we get rid of it? Well, it turns out that for the ghost data, we're going to be able to prove blah, blah, blah. Find this here one second.